Fantastic. So my name is Zach Shwira-Conti, and I'm a research associate at the Alan Turing Institute here in London. I would also like to introduce my colleagues and co-hosts for the seminar series. And these are Andrea Pizzaferato, who is a visiting academic at the Turing and also at the University of Bath, and also Davor Donovic, who is a PhD enrichment student at the Alan Turing Institute, also here in London. So for those of you who are not familiar with the Alan Turing Institute, or the Turing as we call it, this is UK's National Institute for Data Science and AI. And on a side note, if any of you in the audience are interested in sharing your work within the remit of physics-enhanced machine learning, we'd be very happy to talk with you and to find a slot for you to share your work with our audience. Right, so as for the format of the seminar, as most of you are now quite familiar with, our speaker for today will talk for around 4 to 5 minutes, and the remaining time will be used for Q&A, which you can do so either by asking in person or via the chat function. So without further ado, I'd like to ask my colleague Andrea to introduce our speaker for today, and I thank you all for joining.
Thank you, Zach. So Dr. Liu is the Grant Design Assistant Professor at the University of Cambridge. He received his PhD in engineering at the University of Cambridge in 2019. He was then a postdoc in the Department of Mechanical and Process Engineering at ETH Zurich, and a postdoctoral fellow in Mechanical and Civil Engineering at the California Institute of Technology. Dr. Liu's research interests include data-driven mechanics, uncertainty quantifications of materials, micromechanics of metals, composites and mechanical metamaterials, as well as function space learning methods. So without further ado, the floor is yours. Thank you.
Thank you, Andrew, and thank you, Zach, for inviting me here. And it is really a great pleasure to present our work today at the Turing Institute. So my topic today is learning-based multiscale modeling, computing data science and also computation. These are the work that we have started when I was a postdoc at Caltech, and we're continuing these works at Cambridge as well. So I'd like to start with a brief introduction of what a normal day of a mechanical engineer would be. So essentially, as a mechanical engineers, we will be giving an application to design. For example, be it that we want to design a steel bridge frame, or we want to design a car body that is impact resistance, or have an application in mind. And we'll then basically need to consider what a class of materials that might satisfy our design task. If we were to design like a high temperature application like turbines, engines, then we might think of metals. If we think about lightweight applications such as airplanes, we'll think about composites. So that is basically the first step that you're going to think before going to do engineering design. But after we have a material in our hand, we need to also consider what would be the structure or the topology of our designs. For example, if we were going to design a bridge, then we'll basically need to do some topology optimization to basically optimize, to basically maximize our the performance of our engineering design. And once we have our shape topology and material system at hand, we will need something that basically links our material system and our structures. And this link is called constitutive model in our field. So it's basically a model that serves as a key that bridges, that describes how the materials would deform, and it will basically then integrate the material models to the overall engineering design. And there are a variety of material models developed over the past 50 or 100 years. Nowadays for different materials, we will have different constitutive models. For example, if we're considering for rubbers, we will think about hyperelasticity. We consider about metals, we'll think about plasticity. So we'll have this kind of constitutive models that we have kind of started from the years experience. Now, if you ask, where does this constitutive model comes from, right? So the classically it comes from experiments. So basically, what we do, for example, in this hyperelasticity or plasticity models, is that we're going to assume or postulate the existence of functional forms of these constitutive models with unknown parameters that we're going to fit from experiment. So, for example, you might simply just do an inbound tensor test to fit out your Young's modulus, and then you can then afterwards use it in your constitutive model and then do the design, right? And now, of course, if you say that I don't want to do experiments, I want to know whether are there any alternative ways to come up with constitutive model. Yes. So we can look at lower scale modeling. So for example, we can go one scale down. So if we're looking at metals, for example, we can go to grain levels, we can look at crystal plasticity, and then we can then conduct the so-called homogenization or procedure or asymptotic analysis to basically then regulate our lower scale models and to basically come up with the parameters that we can use for the larger scale, for the constitutive model in form, right? And then if you ask, okay, so it seems nice, but where does this lower length scale model comes from? Then it can then either comes from, for example, experiments. So we can now done micro scale experiments. For example, we can do mechanical tests in the grain level. For example, we look at, for example, these are some of the material scientists' favorite work. They're looking at the distribution of precipitates, and then you can then figure out what would be a proper grain level micromechanical model would be, and then you can use it to then come up with a macro scale concept model. Now, of course, if you again don't want to do experiments, then you can do another scale down. You can look at the molecular scales. You can, for example, do molecular dynamics, and then you can repeat this procedure again and again and again until you end up with first principle, and that would be the quantum mechanics, right? So this is basically then come up with a general framework of mechanical design or multi-scale modeling, in the sense that we can use either experiments or lower length scale models to inform our models, and basically to include by this process. We can, of course, also include more and more physics using this lower length scale modeling or multi-scale modeling procedure, right? Now, my topic will basically then focus on this graph. And associated with this graph, I would like to discuss with you the 3 questions or 3 challenges in terms of applying this multi-scale modeling framework to solve real engineering problems. Now, the first challenge is that it is very nice for us to use lower length scale models because it reduces the number of assumptions that we would need to make, or the number of experiments that we would need to do. However, these lower length scale models are, if not always, very expensive to solve. And I will give you an example in 2 minutes. But basically, the first question is, can we then accelerate the solutions of these lower length scale models so that we can use them to basically our multi-scale modeling framework? So that's the first question I would like to discuss. Now, the second question is, even though we now have a high fidelity, relatively inexpensive low length scale models, how can we basically then pass our informations between these length scales, right? So it is, the theory of mathematical theory of homogenization provides us a way, but in practice, there are still certain difficulties that associated with this, and I will explain this in my talk in a minute as well. And the last question that I would like to discuss is, with this multi-scale modeling kind of framework, in each length scale, we're going to have some sort of source of uncertainties generated, and it's going to basically propagate through the length scales. And then the question to ask is, how can we quantify multiscale uncertainty in engineering design? And how do we understand that? How does this uncertainty propagate? And it manifests from a low length scale all the way up to our macro scale applications. All right. So I would like then now to start with my first topic, which is considering accelerating the low length scale models. Now, as I said, the idea of why we're doing all this is because, in our community is called computational solid mechanics. We really want to reduce the number of experiments we need as much as possible by replacing those with high fidelity network models. The key challenge is that we really, these low length scale models are extremely expensive to solve. And just to give you an idea, if we want to solve a micro scale metals, basically they are what we so-called three-dimensional polycrystalline crystal plasticity models. Basically, we model every grain of the metals in the micro scale. Then it will take you 1 to 2 days of computing time in modern high performance computing, but to basically resolve all the details. Now, if you want to go one further length scale down, you're now going to go to the single crystal scale, looking at to model the discrete dislocation dynamics. Then and to track the motion of every and each dislocations. And that simulation can easily take up to 1 to 2 months to finish one single calculation. And to this end, if we were to basically link all the scales and pass in the informations, it would just take us 4 hours. It's just computationally too expensive to do this. Now, the question that we're asking is, can data science help? Can machine learning help us to accelerate this procedure? Now, the answer is yes. But before I dive into details, I'd just like to put one step back, and let's look at the governing physics across all these length scales. So in this plot, I'm showing you in terms of solid mechanics, the important length scales in the x-axis, and the models and theories that we have developed in the past years to basically model these physics. For example, you can see that if we were in the subatomic scale, then that is EFT. Then if we're into the micro scale, then that's crystal plasticity. The unifying feature behind all these models and theories is partial differential equations. For example, if we look at our macro scale model, then basically the finite element method we're solving for continuum is basically a wave equation, right? It has a form showing here. And if we're looking at, for example, the phase field method, right? We consider the subgraph features, the phase changes, and that basically resembles a diffusion type of model. And if we were going to basically look at the molecular dynamics, then that's a bit more challenging. And based on what kind of theory you use it, you can end up with, for example, a stochastic differential equation where your PDEs have some stochasticity there, right? So, but nevertheless, you can see that, the one thing that unifying all this physics, partial differential equations, and therefore, in our study, we start with to ask ourselves, how can we basically accelerate the solution of PDEs? Now, if we look at the conventional way approach of solving partial differential equations, then normally what we have is we'll have a given an initial boundary value problem. I'm showing here, for example, this is a continuum problem formulations, and in order for us to solve this initial boundary value problem, the conventional approach is that we're going to solve with an approximation of the solution field. So, for example, if we were going to solve it using finite element method, we're going to basically write down our solutions in approximate using polynomials. If we were going to use the so-called physics informed neural networks, then we're going to basically parameterize our solutions using a neural network. And after we have this approximation scheme, then we're going to plug in this approximation scheme in the weak formulations, and then we can solve a system of linear equations to find the unknown parameters And then we're going, and then basically we solve the unknown solutions, and then we basically solve part of the differential equation. Right. And of course, the advantage of solving a partial differential equation is that we are solving it because then we know that our arrow is bounded and we can solve it to arbitrary accurateness. However, the drawback is that if I now change one of my conditions, for example, I change the parameterization of my PDE. For example, I change the C here, which is a coefficient entered into my PDE system, or I change my boundary condition or initial condition, then I would basically need to resolve this partial differential equation from the beginning. I need to repeat 1, 2, 3, right? And of course, a further constraint of solving a PDE is that we need to know the Gaussian equations explicitly. There's little room for discussion with respect to when we solve it, we need to know what are the Gaussian equations explicitly. So this is the classical way, and what we are proposing is called learning a partial differential equations. And the key idea is that we consider a solution of a partial differential equations as an operator that maps the input space of the quantity of interest. It can be, for example, PDE coefficients, and that basically in the application domain would means different materials, or we can think of different boundary or initial conditions. So these can be our input states. And then we're interested then to learn the solution map operator that maps these coefficients or boundary conditions of PDEs to its solution. All right. So in that regard, what we're going to do is that suppose we are given a data, which is given a pair of X's, which are X's is our coefficients or boundary conditions, and we're trying to basically learn the solution operator side dagger that maps the Xc to our solution UN, right? And we basically by doing this, what we really want to do is basically construct an operator approximation that given our PDE coefficient, it will basically approximate the true solution operator side dagger. And we would like to do this using a neural network or neural operator that I'll discuss in a minute. So, and you can see that the key difference is that we're now not solving a PDE, but learning a PDE means that we're going to try to learn a family of PDEs that is parameterized by its coefficient. And the way we're going to do this is that we're going to assume that our training data of our neural operator on the network is drawn from a probability measure that defined on top of our unknown parameters. And we're going to try to learn this side dagger condition on this probability measure. And of course, if we were to do this, it will require training data. So we're not, we cannot do this without, if we don't have data but only have PDEs, it's going to be hard for us to do this. But if there are data which are sampled from this distribution, then we can do it. Okay. So I'd like to also have discussion on how we're going to construct this solution operator. And as I just said, kind of indicated, the popular way of doing this nowadays is using a neural network. And if we take a closer look to the architecture of neural network, you can see that it's really very kind of simple idea. So a neural network basically works is basically an approximator that maps between finite dimensional Euclidean spaces. So given a input V and in RP and U in RQ, which are both Euclidean finite dimensional Euclidean spaces, what a neural network does is that it first applies a global linear affine transformation to the input, and then it will apply a local nonlinearity, which is, it can be the symbolic tangent function, can be sigmoid, can be ReLU, and the combination of the global linear affine transformation and the local nonlinearity will then form the so-called a layer of a neural network. right? The so-called then deep neural network or deep learning is that we're going to basically compose this global linear affine transformation and this nonlinearity again and again and again. Of course, each layer will have its own parameterizations, which can be equal or not equal to the previous layers. But you can see that the idea is that we're going to compose these two operators again and again and again so that we increase our length. Now the so-called, and this is this composition that gives us the approximations, neural network approximations, and the so-called learning is basically a minimization task where we're trying to minimize the loss function, which is measures the difference between the data, which is UI hat, and the neural network prediction UI, and we're going to optimize this against our parameterizations A and B. So this is a nice kind of a summary of how classical neural network works. However, this thing is has shown successful in image classification, in language applications, but a key difference from what the physics and the problem of physics and those in the images or language process is that in physics, in partial differential equations specifically, we're dealing with functions and unknowns that is continuous. So, and in that regard, we're dealing a problem by its very nature has infinite dimension, which is quite different from just approximating within finite dimensional Euclidean spaces. So, so therefore, one of our driving idea is, can we extend the idea of neural networks and make it work in the infinite dimensional spaces? In that regard, that would mean that if we can construct architecture in function spaces, then that would mean that we, it can become resolution independent, meaning that I can train it in one resolution and then I can just use it in all other resolutions without the need of the training. So that's the key idea and motivation of this. It turns out that we can, and we come up with the so-called neural operator architecture, and which does exactly what I've said. So the key idea behind this is that if we look at what the architecture of a classical neural network, you can see that the key thing that we're going to do is that we're going to apply a global linear affine transformation to our input in each layer. So that's the first step. And the idea that the way that we're going to extend it is in the so-called neural operator, is that we're going to replace this global linear affine transformation to a global linear integral transformation. So in that regard, we're going to basically construct a kernel, Ki theta, and we're going to basically replace this Aij Vj on this matrix multiplication by day with this kernel integration formula. And we have tried or come up with a lot of different kernels to construct this to be used in this neural operator scheme. So we have tried graph neural operator, we have multiple graph neural operator, we have low rank neural operator, we have Fourier neural operator. So all of these are basically different kernels that we applied, functions that we applied to approximate this global linear integral transformation. And once we have this, then we're going to again to compose this with the nonlinear, the local nonlinearity, and then we're going to construct our neural operator approximation scheme again by composing this global linear integral transformation with nonlinearity as a layer, and then we're going to compose it again and again to make it deeper. So that's the idea of neural operators. And today I will be basically focusing on a very successful architecture that we have found, which is called Fourier neural operator. So the idea of Fourier neural operator is that we're going to basically replace the global linear layer with the so-called Fourier layer. Now the idea of the Fourier layer is basically that if we were given a input, and we're going to basically first, we're going to first conduct a Fourier transform our input, and then the key idea here is that convolution in the real space is basically a multiplication in the Fourier space. And therefore, after our Fourier transform, we're going to basically learn the neural network parameterizations in our first space. And that is basically a single multiplication that is very easy to learn. And then we're going to basically do a inverse Fourier transform after the multiplication in the Fourier space, and then we're going to basically then that will bring us back to the real space, and then we do our nonlinearity, as I said, this basically then becomes a proper Fourier layer. So we have tried this architecture to a bunch of PD scenarios. So for example, what I'm showing here is a solution of 2D Navier-Stokes equation. So this is basically a velocity versus streamline vorticity kind of type of 2D Navier-Stokes. I'm showing you the two cases with different initial conditions, and in this, in the left two panels here, I'm showing the vorticity plot of the field predicted using the numerical solvers, and in the right panel, I'm showing you the prediction using the this learned by the Fourier neural operator. And you can see that the arrows, they're looking quite same, and the important thing here is that the FNOs Fourier neural operators is 1,000 times faster than traditional solvers. So that really saves us a lot of time. And we have also compared our Fourier neural operator solutions with a bunch of popular neural network or neural operator approximators, and you can see that in all the cases, FNO has basically the lowest error. Plus, the benefit of constructing something in function space is that you can see that in all these cases, we have trained our neural operator approximation at a low resolution, which is somewhere here. In this case, I believe this is here, and then you can see that we can then, when we test it with other resolutions, you can see that this approximation error is a constant. If you're going to use a fully connected neural network, you can see that the error kind of increases as you stay away from your training resolution. So that's basically the power of function space learning method. So and really the idea is that we can show that we can really achieve the so-called zero-shot super resolution. So that the idea is that you don't need to retrain it. You can just train it on one resolution, and then you can use it to other resolutions without the sacrifice in terms of the approximation error. And that brings the end to my discussion of the first question. And now I would like to draw your attention to the second question. Is basically how are we going to bridge the scales between the length scales. And if we think about this question, right? So how the bridging problem, then by its very nature, this is a dimension reduction process. So basically, when we move from a low length scale to a higher length scale, what we're basically forgetting a lot of detailed informations, and we're only going to try to capture or do a partial observations of the interesting variables. And to that end, a natural thing would come up is memory, and let me show it by example. So picture a one-dimensional material with two composites. So I'm showing you here. So this blue and yellow, blue and green are two composites. Are two different materials, and the governing equation is shown here. So basically, I'm considering a material with viscoelasticity. So in this micro scale, these are all viscoelastic, and you can see that because it's viscoelastic, this material itself is what we call Markovian, meaning that the material response at time t is only a function of its strain at time t and strain rate at time t, meaning that this the microscale physics has no history of path dependency, right? However, if we were going to look at a macro scale, so we're going to look at a scale which is much length scale which is much larger than this, we're going to see that after the homogenization procedure, you can see that the homogenized stress has very similar to the micromechanical models. So it has the so-called elasticity, it has the viscoelasticity. However, and these two are Markovian, but however, it has had an additional memory term. You can see that this is basically the boundary condition involves with this beta is something determined by the material parameters in the micro scales. You can see that even though that our micromechanical model, the low length scale model, is Markovian, has no path dependency, the minute we jump between scales, we're going to introduce memory, meaning that and the key reason behind it is that we're doing a partial observation of the system. We're forgetting a lot of the details, and therefore, if we were to construct a proper multiscale models, then that multiscale model should have path dependency as well. And in other words, the operator side diagram that we're trying to learn has to take all the informations of the path deformation or the deformation informations into our inputs and map that to the stress output. So that is the kind of the key challenge here, is that how do we incorporate this memory into our models? And I mean, this is becomes part of standard question in the mechanics community, and it turns out that people have sort of ways to address this, and a classical way of addressing this is the so-called internal variable approach. So this is introduced into thermodynamics by Saga in 1931, and it becomes a basis of modeling inelastic material behaviors in our community. So basically, what we do in the internal variable approach is that we're going to expand. We know that the material is history dependent, but we're going to basically make it a Markovian by basically include internal state variables. And in this, for example, in this 1D example, so this convolution structure can actually, I can write this convolution operation as a state variable C, and because of this special convolution structure, then I can conduct that the state variable is going to evolve by this. There's a evolution law of this, and that's basically states that C dot is just minus k C plus E of t. So that basically you can see that the box on top and box on bottom are completely equivalent. And this is basically the key idea of internal variable approach. So basically, we're going to say that we're going to use an internal variable to represent a history of path dependency or memory of the material. Now, this of course becomes massively successful, and it's a standard basis of physics. However, the criticism of this approach is that in practice, this is really a phenomenological approach, in the sense that the choice of internal variables is often ad hoc, and we don't know that whether we have choose enough state variables to describe our system, or we have choose more than enough state variables to describe our system. And to that end, there's no notion of convergence, basically. So therefore, it can be either insufficient or redundant. But this kind of approach really inspires us, and we can see that, okay, so when we ask our question, can we then learn these internal variables from data using deep neural operators? So that inspires us to come up with the so-called recurrent neural operator architecture. So basically, again, we're interested in the mapping from the whole deformation path history, which includes all the history from 0 to time t, and we're trying to learn the map learn the current stress output at time t. Now, the goal and the way we're going to construct this is that we're going to basically extend our input space using this internal variable X's, which are we basically say that we make no assumptions on the evolution law on it. We just assume that this X's exists and there exists a first order evolution laws of it. And then we're going to use the new operator architecture to approximate this mapping G that maps my strain at time t, internal variables at time t, and parameterized with theta 1 to the evolution of my internal variables. And then we're going to learn an extended constitutive law, which takes not only the strain at time t, but also the past history, which is now embedded in this state variables as my input, and learn that to my output stress. And to that end, what we're really trying to do is then we're going to then call the combination of G and F as to be our psi, and then we're trying to use this to approximate the psi dagger, which is my operator of interest. And we're asking ourselves now, with this kind of structure, we're asking ourselves two questions. So are there a minimum number of the dimension of C's, or the number of state variables that we can we require for model this memory, and can we somehow deduce this from data? And also the second question to ask is, can we learn the hidden dynamics, this operator G here? Can we learn it from data without the need of making a priori assumptions on how these state variables will evolve? It turned out that we can, and again, I'm going back to this beloved 1D example. So if now we're thinking of not a two-phase material, but we're thinking about an L-phase material, meaning that we have a material made of L phases, then there's a nice theorem that we proved is that if you have L-phase material, then the number of state variables, the number of convolution term you end up with your truth operator psi dagger would be L minus 1. So basically, if I have L phases, then I need L minus 1 state variables to completely describe its past dependence on history. And what I'm showing you here in the right figure is the test error of our RNO with respect to number of initial state hidden variables we put in the architecture. You can see that if we are not going to put any state variables in our architecture at all, then our test error is huge. So that means that there's no hope that we can explain the data at all. However, if we put one state variable there, then it dramatically the error dramatically decreases to approximately above 10. And then if we put two state variables there, then this arrow then suddenly just reduced to about 2 or 3%. And afterwards, no matter how many state variables you're going to increase, our arrow is basically stays approximately the same. So that's a way basically we're starting to see the behavior of convergence, and it seems like after the two state variables, our test arrow seems to be converged. And this suggests to us that to completely describe the class dependency of this problem, we need two state variables. And that actually matches our theorem, because in our theorem, it predicts that if I have a three-phase material, then I need two state variables. So these things kind of nicely matched. And importantly, we can also show that our system learns the truth evolution law of the state variables. For example, we know that from our theory that the evolution law is given of the state variables given by a linear ODE shown here. And when we plot our truth evolution law and what we have learned from neural network, from the recurrent neural operator, we can see that this thing matches the evolution of state variables matches actually quite well, right? And that basically tells us there's some hope that we can actually learn the true hidden fit dynamics from our data. And we later then just extend this to a 2D and 3D more challenging problem. So we're now considering the so-called crystal plasticity model. Is a kind of complicated model in our community is basically the idea is that we have an aggregate of polycrystals showing in this little represented volume here. And each of these polygons are the so-called one grams, and within each grams, it is governed by a system of partial differential equations presented here. So I'm not going to go into the details of the governing equations, but just try to tell you that this is, the PD governing within each grams, the governing PD is kind of is a nonlinear path-dependent PD itself. And so the idea here is that we're trying to then apply the same approach that we did in the 1D case and trying to see whether we can learn governing state variables that governs this problem. Now, it turns out that we can, and it does works quite well. So I'm showing you here a 2D case where we consider, so we have a two-dimensional polycrystal plasticity, and you can see that we can, with this using this recurrent neural operator architecture, we can learn the homogenized stresses quite well. And I'm showing you here, this is our periodic boundary condition of our inputs, and this is the stress outputs. And the solid line is the true solution, which we solved using numerical solver. It's actually fast Fourier transformed. And the dotted line is our recurrent neural operator prediction. And you can see that these two lines agree with each other pretty well. And more importantly, what we have found is that for some reason that we are yet to understand, this learned approximators also works when you have data withdrawn from a different probability measure that are used to train it. So for example, here we train our recurrent neural operator using random loading process, because these are a smooth version of random walks. And then when we test it using the so-called mechanical relevant loading process, so these are deterministic process. This is the so-called tension, this is tension compression, this is cavity expansion. So these are deterministic functions. And you can see that, we are still kind of providing some sort of guaranteeing that bounds, the guarantee of error bounds. You can see that this error are not going completely off. And an additional benefit of, again, training using this function space method is that, for example, here we have our train resolution, which is we train this our approximators with resolution 100, and then we test it with all the different resolutions, and you can see that the recurrent neural operators has a very benign behavior when we increase or decrease our test resolutions. However, if you were use just a recurrent neural network, then you can see that the minute you move away from your training resolution, the error just becomes terrible. So, and therefore, is again, as I emphasize, that this is the benefit of constructing approximators in function spaces. So, and we have then just, to demonstrate that we have really can achieve this multiscale modeling, I'm showing you a real multiscale models where I'm showing you a study of impact of the plate. So we have a projectile at the top now impacting a magnesium plate, which has its microstructure is described in here with these governing equations. Now we're using the learned recurrent neural operators at each point as our constitutive model, and this is what we get as a result. So what we have found is that if we use this recurrent neural operator approximations as a surrogate model to a faster Fourier solver, and we basically end up with 10 to the power of 6 faster than the FE square, which is a conventional approach. So that really, gives us a lot of confidence that using a neural operator approximators is a really promising way of addressing these challenges. Now, with this ends the second part of my discussion, and I understand that there's not much time left, but I'll briefly discuss the third topic, which is on the uncertain quantification per stack. So basically, as you can see that, with this multi-scale modeling framework, there are sort of uncertainties from each scale, and they're going to propagate as we conduct our multi-scale modeling practice. So the question to ask is how to quantify the propagation of these uncertainties. And the idea that we're going to do this is that we're going to basically think of multi-scale systems using maps and subsystems, basically. So we think of our material and component model as a map from parameters that specify the material and geometry to a design or an outcome y. So we think of our full system response to be y equals to a response function f, takes input of uncertainties, could be either from parameters or geometries as x1 to xn, right? And we're interested in, so first the question is uncertainty quantification. So how do we quantify uncertainties in input x, I that affects uncertainty of output y? And the second question is, if we're going to do material by design, what is the consequences of changing input x that result in us to get to obtain a design of output y? And the challenge of doing this is that if we're going to do it in a broad brute force way, we're going to use for example, use a Bayesian method using Markov chain. These are basically, too expensive to evaluate directly. So we're asking this, are there a way that we can break down this, do some sort of divide and conquer approach so that we can reduce our computational efforts? And it turns out that we can do this, and the way and the method or the theory that allows us to do this is called concentration measures. And to be more specific, there's some theory called McDiarmid inequality that allows us to do this. And the idea behind this is that because of this multi-scale modeling, this nice hierarchical structure, we can use this McDiarmid inequality recursively, so that effectively we can decompose the diameter of this McDiarmid inequality by only looking at subsystem uncertainties. And there's a nice theorem that allows us to do this. Basically, it says that if we can decompose a system level map into subsystem level maps by looking at something called modulus of continuity, and this modulus of continuity would allow us to basically looking at one time, only looking at a subsystem, a particular length scale's response, and then we can afterward we can just compose our response nicely using the theorem shown here. I'm not going to go to the very details of this theorem, but I'm going to impress you with the results. So for example, here I'm showing you a multi-scale impact of a magnesium plate. So at macro scale, we have a ballistic impact. We have a ball impacting a plate at our macro scale. And then in the middle scale, we have a bunch of polycrystals. So if you look at the microstructure of materials, these are metals. They have polycrystal microstructures. And if we then move in another length scale in the micro scale, we have single grains. So each of polycrystals are made of single grains itself, so that therefore there's basically three skills involved in this study. And let's say we have uncertainties in the ballistic performance. For example, the maximum, so the measure is maximum backface deflection. So if I impact the ball to this plate, how large the backface deflection would be. And the source of uncertainty we have is on the single grain level. So in the bottom, in the most refined scale, we have uncertainties on the single grain strength. So for example, we see here, we see that we have uncertainties in the slip strength, crystal resolve series strength on single crystal slip. And using this McDiarmid inequality combined with this theorem of modulus of continuity, we can show that we can really characterize how this single grain scale uncertainties will propagate through different length scales. For example, what I'm showing here is a ranking of is a decomposition of the modulus of continuity, basically the uncertainties that would cause by moving from micro scale uncertainty to middle scale uncertainties, you can see that the contribution of different grain system uncertainty, different grain system will basically how they will propagate to the middle scale. And here I'm showing you how the micro scale uncertainty will propagate to the macro scale uncertainties. And you can see that this method is nice because it provides a way for us to do rankings. Basically, you can see that here the uncertainty in the pyramidal slip and the prismatic slip and Badal slip. So the first three uncertainties is perhaps more dominating than the uncertainty in this tensor twin system. So that is basically provides us a way to basically quantify how these uncertainties will propagate throughout length scales. And with this brings me to the summary of today's talk. We have come up with a general framework for multiscale material structure by design, and associated with it is three questions that we have looking at. So one is how do we increase the speed of solving the low length scale models? And to that end, we have introduced a neural operator learning framework, and a particularly successful architecture is Fourier neural operators for fast PD solutions. And in terms of how we can efficiently bridge in between the scales, we have introduced recurrent neural operators that can not only provide us with an efficient surrogate model, but also give us some kind of ideas or indications of what we are learning, the hidden state variables and their evolution laws. And lastly, in terms of how we can quantify the uncertainties throughout length scales, we can utilize the fact that multi-scale modeling has this nice hierarchical structure. Then we can come up, we can use this hierarchical uncertainty quantification method so that it will provide us a way of estimating how the uncertainties will propagate through the subsystems all the way from the low length scale, from the micro scale all the way to the macro scale. And with this, here is a list of references I've used to prepare for this talk. With this, I would like to end here and thank you all for attention.
Thank you very much, Burigede. It was very, very comprehensive. Thank you so much.
Thank you.
We have claps from the audience. In the meantime, I'd like to open the floor for questions. We have around 5 minutes. Let's see. We have a hand being raised. So, Carlos?
Hi. So super interesting talk. I actually have a few kind of like small questions.
Sure.
When you talk about super resolution with a Fourier neural operator, for the best I understand, it works basically by using the FFT as the discretization. So how exactly, because the FFT obviously needs a regular grid. So if you change the size of the grid, how do you adapt the weights of this R matrix, for example, to like, let's say that your input now is like a 64 instead of like 128 grid?
Yeah, great question. Yes. So the key trick here is that yes, FFT can work on any grid, right? You know, with a 6 by 6 I can do FFT. But then the trick here is when we're in this in the frequency domain, we're saying that in the physical problems we're not most of the time we don't care about higher frequencies. So the idea here is that we're going to throw away the higher frequencies, and to a particular we're going to keep the lower frequency responses, and we're going to basically throw away the higher frequencies, and we're going to learn our the neural operator parameters that only associate with those lower frequencies, right? And then afterwards I can do a inverse Fourier transform. And basically and to that end, it doesn't matter what is your input resolutions, because as long as we're in the Fourier domain, I'm going to basically forget a bunch of higher resolutions responses, and we just put it back to 0. And then we're going to then do a inverse Fourier transform. So in that regard, that is a way of keeping the resolution independence. I'm not sure if I answered your question.
Okay. Yeah, I suppose that then connected to that, so then that means, because let's say that you have initially like 128 modes and you cut that to like whatever, like 20 modes.
Yeah.
But then when you do it with like, let's say when you start with a grid that is like 64, even if you cut it to like 20 modes, those modes won't be, let's say, at the same frequency, right? Because like the Fourier transform, like if you're taking, let's say, the same interval and splitting it in like like 64 instead of like 128, your 20 lower modes won't be the same 20 lower modes than the 128, if I understand correctly.
Yeah, but I think you're right. But I think we're basically rank ordering the first 20 lower modes, and we're just only focusing on that first 20 lower modes, basically. So in that regard, we're always going to keep the same first 20 lower frequency modes. So okay. that's the way that we're going to.
Okay, and if I have time for a second, kind of like slightly unrelated questions. So when you were talking about the 1D viscoelastic beam, you mentioned like sweeping the number of state variables to see what is the minimum that you need to be able to converge. In this case, what will it mean having 0 state variables? What will be then the kind of like input to the model?
So you're asking what would be the input state variables to the model? Is that?
Yeah, because I understand that like the state variables could be like, I don't know, in a simpler model, let's say of like, I don't know, like a string vibrating, you could take like the displacement, or you could take the displacement and the velocity. But like when you have 0 state variables, like how does that work? What is kind of like the input to the system?
Oh, I see. So we're not making any, we're not picking any state variables ourselves. We're making this fully kind of integrated, meaning that the state variables, whatever it is found, at the moment it does not come from a physical understanding. So basically, all our assumptions that in our neural operator approximators we have state variables that is that does not at the moment link to any physical meanings. It's just there, and we presume that this thing exists, and we use it as an input now to our architectures, and with a evolution law shown here, and that is again another neural network. All right, so now we can basically compose these two neural networks, so combine, and then it will then just give us the stress output. So basically, I'm trying to say is we're not a priori specify the physical meaning of these state variables. Rather than we just assume this exists, and if this exists, we can just then put it in our neural network architecture and let the data to tell us what are this and how they evolve. I'm not sure if this answers the question.
Okay, I think I kind of get it. I'll probably have to read the paper to figure out like the details. Thanks a lot.
All right, thank you.
Thank you very much, Carlos. Ulrich?
Yeah, thanks for the great talk. I have two questions. The first is, can you tell us a rule of thumb how much training data you need to train such a neural operator?
Oh, thank you. Great question. So
the second question, or maybe first answer the first one, right?
Oh, sure. Sorry. It depends from problem to problem. But if you're going to ask a rule of thumb, I would say it typically, so these are typically trained with, so for example, all the examples I'm showing here today are trained with approximately 1,000 samples, with the exception that for this 1D case, this can be trained with a few, 50 to 100-ish samples. For the 1D case, it's quite easy. And also, the reason I'm saying this all depends is also the key thing that governs the complexity, the number of data you need for this is the probability measure you use to draw on your data from. So if if your data is kind of drawn from a very complicated probability matter that it has singularities, like in the function spaces, that requires a lot of training data. But if you're going to use, let's say, you're going to basically draw this probability image is a constant, just like a Dirac matter. Basically, you're just going to have all the data is from one distribution, and then you need just one training samples. So basically, it's also associated with that, and also associated with how difficult to approximate the size dagger. So, but just to give you kind of it's really hard to say how many we need before we train it. But I would imagine that for a 2D PDEs, we need thousands of samples. If you were going to train a 3D complicated PDEs, trying to learn the solution operators, we're probably looking at, I don't know, few thousand to 10,000 samples in that range.
Mm-hmm. Thank you. So the second question is in the uncertainty quantification part.
Yeah.
You talked about this concentration inequalities.
Yeah.
And I was wondering what happens there when the solution is ambiguous. So for the posterior distribution is multimodal, for example.
That's a great question. But before I answer, can you elaborate on what you mean by the solution is ambiguous? You're meaning that we're getting set value solutions?
Yeah, so for example, if you look for parameters that exhibit a certain behavior, then different combinations of parameters may have the same behavior.
Oh, right. Then I guess that you mean that the mapping is essentially many to one. Is that what you are?
Yeah, so the mapping from X to Y is many to one, and then the measure does not concentrate like in the inequality around the mean, right?
Yes, and that to that end we can. So basically, the idea is that this is a bound. This is not optimal bound. So this is just an upper bound to the uncertain quantification. So there's with this case, the key difference between this approach and the Bayesian is that we don't make any assumptions on the priori distributions, and therefore we can only provide a upper bound to it. And the thing that really matters is the so-called diameter parameter. Here is basically trying to quantify what is the maximum, what is the maximum difference that you can get from by the maximum change of the response you can get by changing the parameters. And to that end, this approach then doesn't really care if it's 1-to-1 or many to one. As long as we can evaluate this DFI, these diameters, we can provide this bound, basically.
Okay, thank you.
Thank you.
Thank you very much for your questions. I think it is past, yes, it is past 2 o'clock. So Burigede, thank you so much for sharing your work with us. And I'll ask you, that's all right, to share your slides so that I could upload them to our website and they'll be available for the audience to revisit. Thank you once again for your time, and thanks everyone for joining. I will see you in for the next seminar. Thank you.